Welcome back to Science Click. Today, the mathematics of general relativity, part 4, the metric tensor. Our model is getting more and more precise. We have built a coordinate system to describe the position of objects. We have defined proper time in order to interpret world lines as movements through space-time. And we have obtained a fundamental equation, the geodesic equation, which predicts the trajectory of objects as long as we know the Kritstoffel symbols. However, a problem remains. Although our coordinates locate points, they do not give us any information about the distances and angles between them. Indeed, the intervals on the grid do not represent the same distance everywhere, nor the same orientation, and this has to be taken into account. To do this, imagine 2 points on the sheet, very close to each other. Knowing their coordinates, we wish to express the distance between these points. At first glance, we could think of the Pythagorean theorem. Calling dx0 and dx1 the differences in coordinates between the 2 points, we might write the square of the distance as the sum of the squares of both sides. But the Pythagorean theorem only applies if the lines form an orthonormal coordinate system. If the grid is stretched in some way, or if its axes are not perpendicular, the Pythagorean theorem no longer works, and we have to find a more general expression which works regardless of the grid we use. Generally, the square of the distance can always be written as a sum of all possible combinations of two sides, multiplied by some numbers. These numbers depend directly on the shape of the grid. In the special case where the lines form squares of side 1, the coefficients are respectively 1, 0, 0, and 1, which brings us back to the Pythagorean theorem. All these coefficients which multiply each combination can be brought together in a table, with one row and one column for each coordinate. We call this object the metric tensor. It is represented as a table whose components allow us to calculate small distances. Usually, this table is called G, and its components are numbered by 2 indices. We can therefore write the square of the distance which separates 2 points as the sum of each component of this table multiplied by the corresponding differences in the coordinates between the points. This formula in particular allows us to express the norm of the velocity vector. To do this, we replace the coordinate differences by the components of the vector. Bearing in mind that the norm of the velocity is always the speed of light, we can write a more precise version of this equation. It is very important to understand that the metric tensor is a fundamental tool in the theory of general relativity. Indeed, before this point, we only had coordinates, abstract numbers, mathematical descriptions which do not represent anything concrete. Thanks to the metric tensor, we can transform these abstract descriptions into real measures of distances and angles. The metric tensor is the key, allowing us to relate abstract numbers to physical geometry. Finally, let's remember the geodesic equation. We saw previously that this equation predicts the trajectory of an object, provided that we know the Kritstoffel symbols. But so far, nothing told us the value of these symbols, and the equation was therefore impossible to use. It turns out that this object, the metric tensor, will allow us to calculate the Kritstoffel symbols. Indeed, we previously saw that the Kritstoffel symbols describe how basis vectors vary along the grid. but the basis vectors are directly related to the shape of the grid. And as we saw, the shape of the grid is expressed through the metric tensor itself. By measuring how the metric tensor varies along the grid, we can thus determine how the basis vectors change, and therefore the Krestovil symbols. Thanks to the metric tensor, we can now calculate the value of the symbols and thus use our equation. When we perform this calculation, which uses the variation of the metric tensor to express the Krestovil symbols, we obtain an expression which involves derivatives of the metric tensor, because we look at how it varies along the grid, but also its inverse, denoted with indices at the top, which is another table quite hard to calculate. Most of the time, however, this expression can be simplified by choosing an appropriate coordinate system. In particular, we can manage to choose a grid whose axes are perpendicular to each other. With such a grid, the expression of the Krestovil symbols is simplified, as it no longer involves the inverse of the metric, but only its components and their derivatives. Supposing that we know the metric tensor, we can now calculate the Krestovil symbols. And using them in the geodesic equation, we are able to predict the trajectories of objects in the universe. Basically, we have a method to describe the movement of a free body depending only on the geometry of spacetime. The geometry of spacetime is embodied by the metric tensor, which alone describes the relationships between real distances and our coordinates. Unfortunately, we still lack a method to determine the metric tensor. In the next videos, we will see how to relate the metric tensor to the curvature and the energy content of spacetime. As usual, let's summarize all these concepts with a concrete example. To begin with, we take the example of the Earth, described by coordinates of latitude and longitude. On the surface of a sphere, with respect to this grid, the metric tensor can be expressed as the following table. The letter R stands for the radius of the planet, and the angles theta and phi are the coordinates of latitude and longitude. This general expression allows us to calculate the metric tensor at any point along the sphere. Wherever we need to calculate it, we just replace theta by the corresponding latitude. And if we want to measure small distances around this point, we only need to sum each component of the table, multiplied by the differences in the coordinates. This sum gives us the value of the square of the distance between the 2 points. That being said, the metric tensor only gives us access to very small distances. If we want to measure a large distance, we have to calculate it all along the trajectory, because the shape of the grid might change from one point to the other. In mathematical terms, this is called an integral, a sum over an infinite number of very small distances. The metric tensor is an extremely powerful tool. From abstract descriptions, namely coordinates, it allows us to measure real physical distances on the surface of the sphere. Finally, we will at last apply these notions to a real spacetime. We look at the simplest example, an empty spacetime in which an object moves. We imagine, for instance, a satellite lost in outer space. To describe its trajectory, we provide our spacetime with two coordinates. Time, t, measured on our clock, and space, x, which measures the position of the satellite along an axis. As its proper time passes, the satellite will evolve along these two coordinates. In such an empty spacetime, the metric tensor takes the following form. This metric tensor is quite simple, especially since it does not depend on the coordinates. It is the same everywhere on the grid. And because it does not vary on the grid, all its derivatives are zero, and therefore all the Krestovsky symbols are also zero. Injecting them in the geodesic equation, this simply tells us that the components of the velocity of the satellite do not vary. The satellite traces a straight line through our coordinates. This particular metric, which describes an empty spacetime, is called the Minkowski metric. The Minkowski metric describes the spacetime of special relativity. It is rather simple in that it does not depend on the coordinates. This spacetime has the same geometry everywhere on the grid. A first prediction that we make with this metric is the phenomenon of time dilation. To do this, we remember our previous equation, which related the norm of the velocity to its components. Using this equation for the satellite, we can express its temporal speed as a function of its spatial speed. This value is greater when the satellite moves faster through space. This means that the faster the satellite moves through space, the faster our time will pass compared to its proper time. The faster an object moves through space, the more its proper time slows down compared to our time. At first glance, the Minkowski metric may seem rather simple, but it is actually very special because the metric contains a -1. This -1 is a strange and fundamental property of our universe. It tells us that the dimensions of space and time are fundamentally different. Let's take our satellite again and measure the distance that separates it from a point in the future. Here, for example, 2 light seconds. If we shift this point in space, we would expect a greater distance, but because of this -1 in the metric, the distance is actually smaller. And the more the point is offset in space, the more this distance decreases. When the point is placed diagonally, that is to say that it's separated from the satellite by as much space as time, the distance between the satellite and the point is strangely zero. An object moving along this diagonal would actually travel no distance through space-time, and its proper time, the graduation along its trajectory, would not pass. This is more commonly called light. Beyond this diagonal, distances become square roots of negative numbers. They are imaginary numbers, and the satellite will never be able to reach such points. Nothing moves faster than light.